continuation to our discussion on MOS capacitor. Today we shall see the capacitance voltage characteristics of a MOS capacitance, and also we shall see the threshold voltage concepts. As we had seen earlier, the metal oxide semiconductor combination forms a capacitor. We have the metal part followed by the oxide part, and we are taking the example of a p-type semiconductor in our previous discussion. P-type semiconductor. As you all know, a capacitor is formed by separating two metal parts with a dielectric. But in this case, we are having a metal separated from a semiconductor by a dielectric, which is a oxide. So that we will have the metal oxide semiconductor capacitor. And we have also seen that at equilibrium, for ideal MOS capacitor, the Fermi level at the metal side is in line with the Fermi level at the semiconductor side. If we just draw the band diagram, this is the oxide, this is the metal side, this is the Fermi level at the metal side. At equilibrium, we will have the Fermi level at the semiconductor side aligned to the Fermi level at the metal side, and we have the conduction band here. This is the Fermi level at the semiconductor side, and since we are taking the p type, we have the valence band closer to the Fermi level, and the vacuum level will be at somewhere here, so that the work function at the metal side is same as the work function at the semiconductor side. Work function at the metal side is given by 5m, and here it is 5 SC. So that at equilibrium, Fermi level is a common horizontal line. Now, when a bias is applied at the metal side, a voltage is applied at the metal side, we will have the Fermi level moving up or down based on the applied voltage. This Fermi level will move up or down based upon the applied voltage. You have to also keep in mind that the oxide conduction band and valence band bends in the direction of applied electric field. The conduction band and the valence band at this interface will bend according to the applied voltage, and the relative position of the conduction band and the valence band, and also the intrinsic energy level remains unchanged with respect to oxide conduction band at the interface, at the edge. The capacitance per unit area of oxide is given by COX is equal to epsilon OX. This OX stands for oxide. Okay, epsilon OX by TOX, where epsilon OX is the permittivity of oxide, and TOX is the thickness of the oxide layer. Under equilibrium, the capacitance of the entire MOS system is due to the capacitance of the oxide layer, capacitance formed across the oxide layer. So, the total capacitance C is equal to COX, which is equal to epsilon X by TOX, and the unit is farad per centimeter square. So, this is in the case of an equilibrium, at the equilibrium condition of the MOS capacitor. In MOS capacitor, there is no current flowing across the insulator from semiconductor to metal or metal to semiconductor under any bias. Therefore, the Fermi level remains horizontal in semiconductor because the current is proportional to the gradient in Fermi level. But a portion of the applied potential drops the semiconductor near to the oxide. Thus, the presence of electric field in the semiconductor near the oxide causes bending of the conduction band and the valence band near to the oxide interface. This bending direction depends upon the applied voltage, the gate voltage Vg. We had already seen the effects of bending and classified into three different categories. If you remember, the categories were accumulation, depletion, and inversion. In case of the p-type semiconductor, accumulation happens when Vg is less than 0, and it moves to the depletion type when Vg is greater than 0, and as we increase Vg, it moves on to inversion. If we redraw the band diagram in case of accumulation, then if we redraw the band diagram in case of accumulation, The band diagram will be like this. Let me clear off the screen. So, at accumulation, the oxide layer with the Fermi level at the metal side will be this, and due to the applied voltage, the Fermi level at the semiconductor level side moves down, so that this distance will be the applied voltage QVG, and the conduction band, the intrinsic energy level, and the valence band. There is a bend upwards when Vg is less than 0. This is accumulation. Now, similarly, if we draw the band diagram for the depletion is happening when Vg is greater than 0 in case of the p-type semiconductor. Now, the band diagram will look like this now. The oxide level and the Fermi level at the metal side. Since Vg is greater than 0, the Fermi level at the semiconductor side will be moving upwards, and the bending of the conduction band is happening, the bending of the intrinsic level and also the bending of the valence band. The bending is happening downwards. Now, this bending of energy band indicates a decrease of Hall concentration, near the interface, and the effective capacitance now will be a series combination of the the oxide capacitance, which we had seen earlier, and this in series with the newly formed diffusion capacitance. Mathematically, this can be written as COX into CD by COX plus CD. If you remember, if two capacitors are connected in series, the effective capacitance will be equal to this equation. Now, we have the oxide capacitance COX, or the capacitance in the oxide layer, and the depletion layer capacitance CD. Both are in series. The charge per unit area in the semiconductor, given by Qs will be mathematically equal to minus Q Na W, where W is the depletion layer, width of the depletion layer, width of the depletion layer formed. And Na, as you all know, since this is a p-type semiconductor, it is the acceptor, the number of acceptor ions, or the doping concentration. Both are same, doping concentration. And we also know the width of the depletion layer is given by W is equal to root of 2 times epsilon phi of S by Q N A, where phi of S is equal to the surface potential, and it is given by EIB minus EIS by Q. What is EIB? It is the EIB is the normal intrinsic layer, and EIS is the level of energy, intrinsic energy level after bending. So that difference, this difference is phi S, and it is mathematically given by EIB minus EIS by Q. And it is evident that the capacitance at this particular category, or the depletion, when the depletion happens, the capacitance, the effective capacitance is decreasing from the capacitance which it had at equilibrium. Now we shall see the third condition, which is known as the inversion. Inversion is happening when Vg is still more greater than 0 when compared to the initial depletion, when Vg is increased further. Now what happens is, the band diagram explains, sorry, this is a straight line, and this is the Fermi level at the metal side, and the Fermi level at the semiconductor side have moved still further up because the applied Vg has increased, Vg, and the inversion is happening. We have already seen there are two levels of inversion. One is the weak inversion. Weak inversion is when the intrinsic energy level just touches the Fermi level, and this is the weak inversion. And when the intrinsic level crosses the Fermi level, that condition is the strong inversion. Now, the total charge in the semiconductor under this condition, the total charge Qs is given by Qn plus Qdm, where Qn is the charge per unit area of electrons in the inversion layer. Charge per unit area of electrons in the inversion layer. As you all know, since Vg is positive, it is attracting more minority carriers. Minority carriers are the electrons, since we have taken the p-type semiconductor. And what is Qdm? Which is the maximum value of charge per unit area in the depletion layer. Maximum value of charge per unit area of depletion layer. We are having a inversion layer here, followed by a depletion layer. So the total charge will be sum of these two. And also, now the phi s, the bending phi s is equal to 2 phi f, where phi f is the difference between EI and EF, which means this is phi f, the same amount of phi f is in the other side too. So the total bending will be equal to 2 phi f. So this is the explanation of or mathematical representation. We are trying to introduce formulas or mathematical equation to explain what we had seen earlier. So in case of inversion, the total charge is the sum of Qn and Qdm, and also this can be written as Qn minus Qna Wm, because we know Qdm is Qna Wm, as we had seen earlier. So we have this equation. Now let's just see the CV characteristics or capacitance voltage characteristics of the MOS capacitor. Since we know the capacitance changes with the applied gate voltage Vg. When Vg is less than 0, this is the area. So initially we have the accumulation. Vg is less than 0 means accumulation. We have C by Ci, where C is the total capacitance and Ci is the oxide capacitance. We had called it COX. Ci and COX is same. And at this point, the total capacitance is due to the oxide capacitance itself. That is why we are having 1. So as we move towards 0, this is moving down because there is another capacitance coming parallel to it. And at 0 we have a capacitance called the flat band capacitance. At equilibrium, though we had taken the Fermi level at metal side is in alignment with Fermi level of the semiconductor side, practically it is not the case. There will be a slight variation before combining the metal and the oxide and the semiconductor. So there will be a small capacitance forming when they are joined, and that will be parallel to the oxide capacitance, and that causes this dip in the capacitance. Now as we move on means at depletion where Vg is greater than 0, this area, we see that a depletion capacitance is coming in series with the oxide capacitance, so that the capacitance decreases further. And at weak inversion, where we are still increasing Vg, we have the minimum capacitance possible for the MOS at inversion, weak inversion. Now the MOS capacitance, this capacitance is due to the DC bias, the applied voltage, DC voltage. Now these capacitance will be given with input, AC input. So depending upon the applied signal, the AC input, the capacitance changes. If the applied AC signal is of high frequency, it flattens, the capacitance flattens, and if the applied AC signal is of small frequency, capacitance increases like this, and if it is in between, the movement will be in this dotted line direction. Now there is another area in the CV characteristics, which is this area. This capacitance happens when we are moving from minus V to plus V in a quick fashion. If we change from minus V to plus V quickly, the capacitance will reduce further because the inversion is not affecting, the inversion capacitance is not affecting. This is due to the depletion. So the depletion layer increases and more depletion capacitance comes in series to the oxide capacitance, and so the total effective capacitance decreases further, and then it stabilizes back. So that is the case of the CV characteristics of a MOS capacitance. Now Now let us see what is a threshold voltage. Threshold voltage in case of MOS capacitors. Threshold voltage is the voltage required to introduce strong inversion. Strong inversion in the semiconductor. Mathematically, we will try to have an equation for the threshold voltage, which is VTH is equal to VOX, which is the voltage across the oxide level, plus phi S. Whatever voltage we apply, we have a voltage drop across the oxide level, that is VOX, which is equal to minus QS by COX. This equation is from the relation V is equal to Q by C, and we know phi S is 2 phi F. Phi F is the difference between the intrinsic energy level and the Fermi level at the semiconductor side. And at the onset of inversion, Qs is equal to Qdm. The onset of inversion, so that we can rewrite VTH is equal to minus Qdm by COX plus 2 phi F. And we also know Qdm, the depletion charge at the depletion, is equal to rho Wm, this is the mobility, into Wm, this is minus Q Na into Wm, where Wm is the depletion width. And we also know Wm is equal to, we had seen earlier, 2 epsilon 2 phi F by Qna. So that by substituting these values for Qdm becomes minus Qna root of 4 epsilon phi F by Qna, which can be simplified as minus root 4 epsilon phi F Qna. Therefore, the threshold voltage VTH is equal to 2 phi F plus 1 by oxide capacitance COX into root of 4 epsilon phi F Qna. So this equation is gives us the threshold voltage VTH, which is the voltage required to introduce strong inversion in the semiconductor.